Action potential is a change in the voltage of the membrane potential that causes it to go from its negative resting state to a positive value for a very brief time. Excitable cells are cells that can be stimulated to create small electrical currents or signals such as muscle fibers or neurons. Positive feedback is the ongoing chain effect that occurs when the rate of a process is working in order to increase the product. For example, when nerve cells are generated, there's normally a leaking sodium channel which then changes the charge of the intracellular fluid, which results in gates opening and then closing and then opening and so on. The resting state is the transmembrane voltage that exists when a neuron or muscle cell is not producing an action potential. The intracellular fluid is more negative than the extracellular fluid as a result of ions like potassium and sodium being present on the two sides in different amounts. The intracellular concentration is negative with some potassium and a small amount of sodium, while the extracellular concentration is more positive with a lot of sodium and a small amount of potassium. The difference in sodium and potassium concentrations creates a want to distribute the particles evenly. However, sodium cannot come inside of the cell to even it out, even though potassium can go outside. This is because the sodium gate is closed while the cell is resting. Thus, the cell maintains a slightly negative charge, which creates resting membrane potential, the general voltage difference across the membrane, while a neuron cell is resting at negative 70 millivolts. The threshold is the lowest amount of stimulating that needs to occur in order for a sensation, reaction, or effect to occur. When a cell is stimulated, depolarization begins to occur. It is a positive change in a cell's membrane potential. When a cell leaves its resting point of negative 70 millivolts and moves up to negative 55 millivolts, it goes through depolarization. This happens because positive sodium ions, called cations, are going through newly opened sodium channels and then moving inside of the cell, making it more positive. Overshoot is the depolarization of the plasma membrane after it becomes positive during the rising phase of action potential until its peak is reached at around positive 40 millivolts. Repolarization is the negative change within a cell's membrane that occurs right after depolarization. It basically returns a cell back to its resting point of negative 77 millivolts by moving positively charged potassium ions, also called cations, out of the cell by using potassium channels, which makes them the intracellular fluid more negative than the extracellular fluid because it is losing positive ions. The refractory period is the period of time after repolarization while a cell is at its resting point, that the cell is incapable of repeating action potential. The absolute refractory period is when the second action potential is not capable of occurring, no matter how strong the stimulus may be. On the other hand, a relative refractory period is the period immediately following the absolute refractory period, where a second action potential is inhibited, but not impossible, depending on the strength of the stimuli. Influx is when positive ions such as sodium flood into the cell by going through an active or open voltage-dependent sodium channel, which allows more and more channels to open until the polarity of the plasma membrane is reversed, which then closes the sodium channels or inactivates them. Efflux, on the other hand, is when positive ions such as potassium leave the cell by way of active voltage-dependent potassium channels, which then results in hyperpolarization as the intracellular fluid becomes more negative by ejecting positive ions into the extracellular fluid. Hyperpolarization is when a cell's intracellular fluid becomes more negative than negative 77 millivolts for a short amount of time as it moves out positively charged potassium ions during repolarization. This results in a cell or neuron being temporarily unable to generate action potential. Sodium-potassium pumps are mechanisms of active transport that move 2 positive potassium ions into a cell and 3 sodium ions out of a cell by way of using voltage-gated potassium and/or sodium ion channels. It takes 1 ATP to move the 3 sodium ions out of the cell because it's moving against the concentration gradient, going from an area of lower concentration to an area of higher concentration. However, it does not take any energy to move the 2 potassium ions into the cell because it is going with the concentration gradient from an area of high concentration to an area of low concentration. Membrane permeability is the ability for a cell's membrane to control the entry and exit of solids and solutions from inside or outside the cell. Voltage-gated sodium ion channels are selectively permeable membranes that allow only sodium ions to pass through a solid structure very quickly. It is the main cause of depolarization and repolarization of nerve membranes during action potential. Voltage-gated potassium ion channels are selectively permeable membranes that allow only potassium ions to pass through a solid structure very slowly. It is the main cause of regulation of the cell's membrane's excitability and repetitive low firing in neurons, as well as the recovery of the nerve fiber membrane at the end of action potential. In this video, you will see an example of how a sodium-potassium pump works. You will see 3 Na pluses enter, and ATP will help transport them back out again, while potassium, 2 of them will exit the cell. What you are currently witnessing is the opening of the activation gate or ion channel, as it conducts electrical current by permitting certain ions to pass through it and therefore cross through the plasma membrane of the cell. On the other hand, the inactivation gate is the closing of an ion channel. It does not conduct electrical current when it is closed, and they are impermeable to ions.